All right, so what are we doing on time? All right, so next we have angular momentum. So conservation of angular momentum. And the result here, it takes a little manipulation to get there, but it's kind of interesting when we do. So here, I'll draw our potato again. Little differential mass, dm, has some velocity v. Now this time I'm going to draw a frame here, and we have x, right? And you could potentially have some surface tractions. Okay, so in angular momentum, it's stated in words, the rate of change of angular momentum is equal to the moments applied, right? And so what's the angular momentum of this differential mass? Is x cross v dm, right? That's the angular momentum of the differential mass. And so for the total body, then we have x cross v rho dv, right? And that's equal to the moments applied, so it's the same thing. I mean, there's only two types of forces, surface forces and body forces. And so for the body forces, we have x. So x is just a position vector, right? Remember, a moment is r cross f. Right? So the position vector x cross rho b dv, and the surface tractions is x cross t ds. All right. Now, I'm going to introduce something new. In addition, to manipulate this further, to simplify it down and see what it looks like, we need to put it in an additional notation. But we have cross products in there, right? We haven't talked about how to write a cross product in terms of additional notation. We know a dot product, right? So the dot product of an vector AB is just AI, BI in additional notation, right? But what about A cross B? So in order to do this, we introduce a special tensor called the permutation tensor. And it's a third order tensor that has components I, J, K. And I'll tell you what it is in just a second, but we would write A cross B is epsilon ijk aj bk. bk. And so what is that guy? Epsilon ijk is equal to 1 for an even permutation. So when I say permutation, I mean a change in the indices ijk, and I'll give you an example of what I mean. Right? -1 for an odd permutation, and 0 if any two indices are repeated. So that's really the only choices you have. So an even permutation would be like 1, 2, 3, obviously in order, right? It could also be 3, 2, 1 in order, okay? An odd permutation would be like 1, 3, 2, or 3, 1, 2, something like that, right? So an even permutation, the indices would be in order, either forward or reverse, but in order. an odd permutation, they would be out of order, and repeated would be any like 1, 1, 3, something like that. And so, if you worked through all the details, you plugged in, yeah. Oh, it is. You're right. So that's not a good example. What's another example? 2, 1, 3. There you go. Thank you. Okay. So you need to know what that is, because we're going to carry this thing along as we do a lot of manipulations. We're not going to actually use it till the very end, and it's really easy at that point. Okay. So if we rewrite this equation now in additional notation, then we have d dt, and there's going to be a lot of indices here, so I'm going to probably go slower, but because I don't want to make a mistake, just miscopying. Okay, so all I did there was just rewrite this in additional notation. Okay. So in the first term, we're going to use our Reynolds transport theorem. And in the second term, we're going to use we're going to use a divergence theorem eventually, but oh, you know what? Sorry. Got confused in my notes. All right, so the first term, we've used the Reynolds transport theorem to go from here to here, okay? But we're going to now distribute, the material time derivative over this x and v, right? So we have all right, so we have that. Well, what is this guy? dxm dt. It's the time derivative of a position vector, which is, there's another name for that. Time derivative position is velocity, right? So this is Vm. So what you have here is the cross product of a vector with itself. What is that? 0, right? So this term goes away. All right? So all you're left with is this guy. So this is your left-hand side. All right. now we have the term that has the traction in it. And we're going to plug in our Cauchy stress equation, right? So now we're going to, for Tn, we're going to, Tn is equal to sigma Jn Nj, right? That's just a component form of our Cauchy stress equation. So we'll plug this in here. Right, and then now we have this, we'll use the divergence theorem. Okay, and so then we'll distribute this divergence operator. And okay, we don't do anything. So this is the first term on the right-hand side. And the body force term doesn't change. So then, putting it all together, we have rho So then the body force term. All right. Now I'm just going to rewrite this equation. I'm just going to move some terms over. I'm not going to change anything. I'm just going to rewrite it and do some factoring. Okay, what's this thing? It's linear momentum. That's the Cauchy momentum equation we just derived. And what's it equal? It's equal to 0, right? So this is conservation of linear momentum, right? So this equation becomes 0 equals to ERMN sigma JN. Now also, what's this thing? This what's that guy? No, this is the partial of little xm with respect to the partial of little xj. This had a special name. We used it a few lectures ago, right? It's the Kronecker delta function, right? So that's equal to 1 if I equal to j and 0 otherwise, right? It's the identity matrix for 3 by 3. Okay, so this is delta mj dv, and this has to be true for any dv, right? So this is equal to Rmn, and the Kronecker delta function, anytime you have it with another term that has a repeated indice, you can pass that indice over for the other one. So I can rewrite this as, so basically I'm going to, you see the repeated indice is j, right? And so what I can do is in the first term, I can replace j with m and get rid of that Kronecker delta function. It doesn't do anything, right? So I have this permutation tensor with the stress mn, right, has to be equal to 0. Okay? Well, if r equals to 1, and remember you can't have repeated indices, right? So if r in this equals to 1, so the repeated ones are m and n. You can't have a repeated indice in a permutation, otherwise it's 0, right? So m and n have to be different. So if r equals to 1, m and n have to be different from that, and what you get is an equation that is sigma 2, 3 minus sigma 3, 2 is equal to 0. For r equal to 2, you get sigma 3, 1 minus sigma 1, 3 is equal to 0. And for r equal 3, you get sigma 2, 1 minus sigma 2, 1 is equal to 0. What does that tell you? It tells you that for angular minimum to be conserved, the Cauchy stress has to be symmetric, right? And so in other words, this is the result. And so, I mean, I know it took a long time to get there, and it's probably not the result you'd expect, but it's kind of cool and simple. And another reason I wanted to go through all this is that this really illustrates the utility of the additional notation, because it would have been very difficult to see that or manipulate it in terms of those vector cross products, right? But if we put it in additional notation, then it's just pretty straightforward manipulation to arrive at this.